Hey everyone, it's Dr. Calkins. Today we're going to show you a little bit of week 12, chapter 10. This is the Electro Chem chapter. So in order to deal with this one, we're really going to break it up into two parts. We have oxidation state calculations and then half reaction, oxidation reduction reactions that we'll do in a separate video, which also may include some of these ideas. So let's try to show you what oxidation state really is. It's kind of like charge in a sense. So if we think about something like water, we have 6 electrons based on its Roman numeral of its family. We have hydrogen that has 1 electron, and then we connect the dots. We did that earlier in the semester. What we're worried about now is electronegativity, and when we look at the most electronegative atom, 3.5 oxygen versus hydrogen at 2.1, what we're really worried about here is who owns the electrons. Well, definitely the one that's more electronegative. So if oxygen starts with 6 electrons, and now it's going to feel as if it has all 8 electrons, 6 minus 8 is -2. So oxygen feels as if it's got a -2 charge, or in our case, an oxidation state. Hydrogen had 1 electron, and notice it has none. So if it had 1 and it feels like it has none, it's going to have that +1 charge, and that makes a neutral compound when you think about both equaling that -2 for oxygen. So the reason that water is neutral as a compound is because those atoms are sharing, not equally in this case, but they're trying to share through those covalent bonds. And because 2 atoms end up feeling partially positive and then 1 that's feeling partially negative, it's kind of like those partial charges or real charges that we saw, but it just gives us an indication of who's being a bully and how much of a bully are they being. So this is one way to do oxidation state calculation, just by looking at electronegativity, giving the more electronegative atom the electrons that they want. An example that shows up in the notes that we can walk through is this one. Nitrogen has 3 bonds, 1 lone pair as we'd expect. Fluorine, 1 bond, 3 lone pairs as we'd expect. We look at their electronegativities. Fluorine's a 4.0, nitrogen a 3.0, and again hydrogen over there at 2.1. So the biggest bully here would be 4.0 fluorine, followed by 3.0 nitrogen, and then the bigger wimps, 2.1 hydrogens. So fluorine gets what it wants. If it had 7, now it has 8, that feels like a -1, and we recognize the halogen as a -1 all semester long. So it's not really that different from charge when you think of it so far. However, because fluorine's being a bully, nitrogen gets what's left over. So sometimes in life, you get lemons and sometimes you get lemonade. In this case, nitrogen, because it's not the biggest bully, fluorine is, it gets what's left over, and it only gets the 6 remaining electrons. So if nitrogen had 5 and now it has 6, it feels as if it's a -1. Has nitrogen ever felt like a -1? Certainly not. We'd expect nitrogen in the periodic table to be -1, -2, -3. We're seeing -1 because fluorine is not being very friendly. So nitrogen feels like a -1, fluorine feels like a -1, which is expected. Hydrogen still, they had 1 electron, now they have none, so they feel +1, so +1. And notice in the NH2F formula, you can break this into 3 pieces. A -1 and a -1 balances with 2 positive ones. So that +2 cancels with those -1s to make that neutral compound. Just like up here, 2 +1s and a -2 made 0. Turns out that process is exactly what we'll do, but through a shortcut kind of method. So let's give you some rules to follow first. So again, this is one way of doing it, but then you need to know how to draw a molecule, and a lot of students may have forgotten that. So let's give you a shortcut. A shortcut is just going to give you some rules. And if you use those rules and a little bit of algebra, you can solve these without too much trouble. So let's show you those rules. The first rule is elements in their natural state are 0. So that's always been the case. Elements have always been 0, once our camera figures out how to zoom. The second rule is hydrogen tends to be a +1 because it gets picked on all the time, having such a low electronegativity. Oxygen, unless it's with fluorine, which is never really the case, is going to feel like -2 because it's the second biggest bully and unlikely to be bullied by anybody else. It's going to give it a once, it's going to get a -2 like it once. So far, these are rules that we've used all semester long. Another rule is that group 1 metals are positive 1. Well, no duh. They've been that for the entire semester. Alkali metals like to lose 1 to be like the noble gases that precede them. And group 2 metals, because they're always going to get bullied, more than likely going to be a positive 2 always, and that's been the case so far. So out of 5 rules, nothing has really changed, and that's good. Our 6th rule is that if you're by yourself, so monoatomic, your monoatomic ion charge is your oxidation state. So for example, if you're sulfur with a -2 is both your charge and your oxidation state. Well, if you're by yourself, your charge is what it is. So kind of no duh again. All the charges need to add up. So all charges or oxidation states must be equal. Well, that just means like up here, a -1, a -1, and a +2 should have made 0. Just like up here, a +2 and a -2 should have made 0. So that's really no major, nothing new, once again. And lastly, it's usually halogens are -1. And they've been -1 almost the entire semester. The problem is usually, that's except for with oxygen, because oxygen is going to bully those kinds of atoms. So those are our rules. As long as we follow those rules, we should be able to solve any problem. So let's try a couple. If we have chlorine, which is elemental chlorine, recognize that here we only have 2 elements. They're the same element, they're in the elemental form. Even if we try to divide these and say if chlorine equals 0, that would be 2 chlorines equals 0. We divide by 2, we still get chlorine equals 0, and that was rule number 1. So nothing too crazy there. However, if we have something like hypochlorite, now we use this rule here that says all the charges must be equal, in this case equal to -1. So now we have a chlorine plus an oxygen equals -1. But we know up here from rule number 3 that oxygen's -2. It doesn't really matter the order of the rules, just knows that you use them. So chlorine plus a -2 equals a -1. Algebra says you need to add 2 to both sides. And when that happens, zoom out a little bit, these 2's cancel. Chlorine over here, negative, and a +2 equals a +1. So chlorine for the first time is being a positive charge, not a negative, and that's because oxygen's a bully. And it's not giving chlorine what it wants. Chlorine gets what it gets. And hopefully it doesn't throw a fit in this case. So let's try another one. We try something like perchloric acid. Notice we got lots of bullies here. Overall equals 0. So hydrogen plus chlorine plus 4 oxygens. We're just adding up 1 plus 1 plus 4. All equals 0. So hydrogen had a rule. It was rule number 2. So again, that was the rule over here. Hydrogen's +1. So plug in +1. Chlorine is got a rule, but it's got a bully, so it doesn't count. So that's like your X in algebra. We have 4 oxygens and -2. That all equals 0. Combine your like terms. So here we have a -8 and a +1. So we have chlorine plus a -7 equals 0. And now we see chlorine by itself only if we add 7 to both sides. Chlorine equals +7, which is crazy to think about because chlorine can be a +1, it can be a 0, and it can be a +7. Well, if you think about it, chlorine loves chloride. And that's an oxidation state of -1. That was our rule that if you're by yourself, your charge is your oxidation state. Now we see chlorine can be, in its elemental form, 0. We see that in hypochlorite, it's going to be a +1, but you can imagine in chlorite, it's going to be a +3. In chlorate, it's going to be a +5, and we just saw in perchlorate, it's going to be a +7. So this is the life of being a halogen atom. Usually, it's going to get what it wants. Sometimes it doesn't have anything because it hasn't found another partner, like a metal or something, to get electrons from. But then if it's getting bullied, it can be whatever it wants. So for everything in the periodic table, Now we have two choices. Chlorine can go in the direction that makes it happy, which is forward, that's -1. It can be elemental chlorine. It can go back 1, potentially back 3, potentially back 5, potentially back 7, and become noble gas-like, but in the opposite direction. So early in the semester, we basically lied to you. We said elements will always do what is easiest because that was what was easiest to think about early in the semester. But the reality of life is we would love to do what's easiest. But sometimes we have to do homeworks and exams that we don't like. We're going to do things that we hate, move further and further away from what we want, and maybe eventually there's a silver lining and we get back to noble gas. That's not always the case either. But forward is still negative, backwards is still positive, and now any element can have exactly what it wants, either forwards or backwards if it's non-metal. So even sulfur can be a -2, but it can go all the way back and be a +6. Phosphorus, nitrogen kind of atoms can go to the -3. We always said they should, but they can also go all the way back to a +5. Things like carbon can go to -4, or they can go to +4 like we said they could all along. So really we're just saying you can go both ways now instead of just one way. In oxidation state and using these rules is the easiest way to do the algebra. There's a lot of practice in the lab that's coming up. So just use the rules, plug them in. Whoever doesn't have a rule, you use for X, and then you solve it through algebra. So hopefully this helps. We'll get some more practice in another video.